But this is an important type of problem that we'll encounter. And it's going to be a limiting reagent problem. So let's take a look at this one again briefly, and then let me just talk about it a little bit here. One of the things you need to do when you're doing these is you have to write down the states. So for example, CH4 is a gas, and then O2 is a gas, CO2 is a gas, and H2O is what? A liquid. That makes a big difference in how we handle this particular problem. We need to know the states. And so when you write a chemical equation, it's not done. I know the book doesn't do this, but the book is geared towards Chem 4. But when you go into Chem 1A, then it's a different story. You have to do this kind of stuff. And so, anyway, like I said yesterday, when we're given two reagents, we've got to figure out which one is a limiting reagent. And so what we'll do is we'll calculate the yield first. So this is going to be the yield from methane. So we're going to do how many? 125 liters of methane. Okay, now in this particular problem, we're after the water. But water is it a gas? Or, no, it's not a gas. So we can't do the volume to volume, or we can't do the liter to liter conversion. Since we can't do the liter-to-liter conversion, we have to do a regular stoichiometry problem. In a regular stoichiometry problem, we do a mole-to-mole conversion. So we got to get this to moles. So there are two ways we can get this to moles. One way is we could use the ideal gas law to figure out how many moles of methane we have, or we could use the molar volume. Which one do you prefer, the ideal gas law or the molar volume method? Well, in this particular example, the temperature is 25 degrees C and the pressure is 1 atmosphere. So you might have the molar volume memorized. Do you have it memorized? What is a molar volume? 24.5. 24.5. You could just do that. And so 1 mole of any gas is 24.5 liters. And so this could be 1 mole of gas per 24.5 liters of gas. So in this case, the gas is methane. So this will tell us how many moles of methane. So we get moles of methane, but this is only valid for gases. So once we have moles of methane, then we'll go to moles of water. It's a 2-to-1 mole ratio. Then once we have moles of water, water is a liquid. And so if we want the volume of a liquid or a solid, we have to get the grams and we have to get the density. And so here, what I'm going to do is I'm going to go from moles of water to grams of water, 18.02 grams of water per mole. And then I know the density because the density is given. It's 1 milliliter of water is 1.00 grams of water. And so we can figure out the yield of liquid water from 125 liters of methane. So we'll do that here. So 125 divided by 24.5 times 2 times 18.02 equals 183.8 milliliters of water. Okay, now if you don't have this memorized, how can we get it? Well, we can get it from the molar volume equation. The molar volume equation is equal to what? RT over P. can get it. In fact, we could get it, the molar volume at any temperature and any pressure for gas. This is just for gas, molar volume of gas. All right, that's the yield from the methane. But we don't know if we're going to get that because we don't know if we have enough air. And so we're going to calculate the yield from the air or the oxygen in the air. And it's going to be 1,150 liters of air. Air is not pure oxygen. What is the composition of air? It's 21%, so that means 21 out of 100. What? Well, here you could either do moles or you could do liters. In fact, let's just do liters because it'd be easier. If we do 21 liters of O2 over 100 liters of air, then we could figure out how many liters of O2 we have. Since O2 is a gas, we could use the molar volume. That is, 1 mole of any gas is 24.5 liters. But it has to be at what? This conversion factor is only valid at it is gas. Let's say that for gas, it's only valid at RT and 1 ATM. If we're not at RT and 1 ATM, then the number is different. So I'm going to put that restriction here, RT and 1 ATM. We can't use the molar volume if we're at a different temperature and different pressure. We'll have to calculate it using this equation. The equation is RT over P. All right, then we get moles of O2, and then we just do a mole-to-mole conversion. That's the heart of the stoichiometry. It's a 2 to 2. So 2 moles of water, 2 moles of H2O for every 2 moles of O2. And then we'll go to grams, 18.02 grams of H2O per mole of H2O. And then we'll go to milliliters. Gram, same thing as milliliter. So 1 milliliter is 1.00 grams of H2O. So let's calculate this one here. It's going to be 1150 times 21 divided by 100 divided by 24.5. Okay, times 2 divided by 2 is the same, times 18.02. So I get 177.6 milliliters of H2O. Right, now I compare the two. If I burn all the methane, I'm going to get about 184 milliliters of water. If I use up all the air, I'm going to get 178 milliliters of water. So what is my yield of water? Do I add these two numbers together? Is that correct? Do I take 184 plus 178 and that's my total yield of water? No. And so which one is it? In other words, which was my limiting reagent? The methane or the air?
The air.
The air. Okay, once all the air is used up, this is my LR, limiting reagent. Once all the air is used up, then I'm only going to produce this amount of water. And so this is my yield of water, my theoretical yield of water. I'm not going to be able to get 184 grams or milliliters. The reason I'm not going to be able to get that is because I don't have enough air. In fact, I'm going to get this. Now, how many sig figs am I allowed here? How many sig figs do I have? Well, this has how many? 3 or 4. This is how many? Well, 21 is how many? 2. This is 3. This is infinite. This is 4. This is 3. So I'm only allowed 2 sig figs, so at 2 sig figs, this would just be 180 milliliters of water. Be the yield. It's off because of rounding error, but so are there any questions about this? No? Today I have to cut out a little bit early. Actually, I'm going to have to cut out early today. And so,